So first of all, we're going to start off by saying, okay, what is a linear equation? So these are basically in the form of the following. So we have some kind of function, the first derivative of the function being equal to, or some kind of equation where you can get it into the form that looks like this. So the first derivative of the function is equal to some arbitrary function, and then we have our actual function that we're dealing with, and then plus another arbitrary function here. Okay, so a of t and f of t, those are like I was saying, those are arbitrary. Those are kind of random. These are the main functions that we're concerned with. Okay, so and there are two like off branches, I guess you could say, of this linear equation. So the first is when f of t, when that function here, this one being added, is equal to 0, then we're just left with x prime is equal to a times x, right? And all of these are, of course, dependent on t. But anyways, so we have something that looks like this, and the terminology for this kind of equation is called homogeneous. Homogeneous, okay? And as you'll see, this is also just a separable equation. So we'll get to that in a little bit, how to solve each of these types of equations. So then the other case is when our f of t is not equal to 0, right? So when it's not equal to 0, then we're left with x prime is equal to a times x plus f. And this conversely is called inhomogeneous. Inhomogeneous. Okay, I'm just going to squish that word in there. Alrighty. So let's start with the homogeneous equations and how to solve them. So if we have homogeneous equations, okay? So this would be of the form when we have x prime is equal to ax, all right? So when we have something like this basically just means that we have dx over dt, because remember everything depends on t here. So then we have our a of t and our x of t, okay? So we can separate these two, right? Because this is a separable equation, so we can divide by x of t on both sides, divide by x of t, and multiply by dt on both sides, multiply by dt. So these x of t's cancel out, as do the dt's. So we get 1 over x of t, and then dx is equal to a of t dt, alrighty? And then here we would just integrate, all right, and we get ln of whatever our x of t is, okay, and then we have the integral of a of t dt, and as we continue and we solve for our x of t, we would just exponentiate both sides, okay, and get basically just, well, we have our absolute value of x of t, and we've gone through this in previous problems as well. We've worked through the whole thing. So we get e to the integral of a of t dt. Okay, and then to get rid of that absolute value sign, then you just add that constant c in there, because there's also a plus c when you do the integration, that is. So we have this random plus c here, and anyways, we just end up with something that looks like this. Our solution, our general solution, looks like some kind of constant a, okay, where a is plus or minus e to the c, e to the integral here, okay, and then I'll just write where our a is equal to plus or minus e to the c, like it has been before, okay? So this is the kind of solution that we would get here, and again, so these are, I'll write the words here, separable, I'll just write separable, because it is separable, right? That means it's a separable kind of equation, all right? So let's do an example of this, of a homogeneous equation. So here's an example. So we have x prime is equal to sine t times x, okay? So see here how we have, this is like our a of t, okay? And x is just x of t, and x prime is just x prime of t. So we can rewrite the left side as dx dt, right? And then we have sine t times x. So when we separate these, we get 1 over x dx is equal to sine of t dt. We're going to integrate both sides, integrate, all right? So we get ln absolute value of x is equal to, and we have a negative cosine t here, and plus a c, of course, all right? And then we're just going to exponentiate both sides, so we get absolute value of x is equal to e to the negative cosine t plus c. Okay, we could separate that out too, so we just have e to the c times e to the negative cosine t, okay? And then finally, to get rid of this absolute value sign, we just stick a plus or minus in front. So we get x is equal to plus or minus e to the c times e to this negative cosine t. All right, and let me just rewrite it on the top here. So we have x of t, that would be, is equal to, and we're just going to replace all of this thing with a, with a random constant, well, not random, but another constant, a new constant, a, times e to the negative cosine t here, and we're going to write as like a qualifier kind of thing, where a is equal to plus or minus e to the c, okay, which is another constant as well. Alrighty, so this would be the general solution to our original ODE, which is right here. Okay, that was our ODE. Okay, so believe it or not, that was the easy part, the homogeneous equations, because they are separable and we already know how to work with those. Now, I'm going to show you how to look at inhomogeneous equations and how to tackle those guys. So we have inhomogeneous, so that means that we're of the form x prime is equal to ax plus f. So here is the process. We're going to start with this equation, right? So we have something that looks like this, and what we're going to do first is just subtract this a to the x, or sorry, a times x. So when we do that, we get x prime minus a times x is equal to f. All right, and all of these things here are functions of t, okay? I'm just not writing the parentheses t because that would take forever and a day. So anyways, so now the concept is, here's where we're going to make a little bit of a jump. So everything on the left side looks a little bit messy. It's just, admittedly, it's messy. So what we want to do is, here's what we're going to do. This is called finding. So we're going to find a mu or a u. You can use whatever symbol you want. But some function of t such that, st means such that, the left side, such that mu times all of this guy, everything that's on the left side, is equal to mu times x, and then to the first derivative. Okay, so this is a leap, I know. It's like, what is this letter? Is that Greek or is that? It is Greek. I'm just gonna say. So anyways, that's called mu. So the thing is, what we want to do is get on the left side, because this is so complicated here already, and we can't just integrate nilly-willy, right? With respect to t. So what our aim is to get this is called an integrating factor, okay? So here's some terminology. This is called our integrating or integration factor. You can say either way, which allows us, and that's kind of like a tool that allows us to integrate more easily or more smoothly, okay? So we're going to find something like this, such that the left side, when we do multiply by it, okay, and we'd have to multiply on both sides, of course, when we do multiply by it, this thing can just be simplified into the first derivative of mu, whatever our mu is, this u thing, mu times x, okay? And then this is going to be equal to mu times f, all right? Because we multiplied by that on both sides. And then this is where the payoff is, because then when you integrate on both sides with respect to t, then on the left side, all you have to do, the integration sign just cancels out the prime, right? The first derivative sign. So we just get mu times x, and that's it. That's way easier than trying to integrate just this guy alone, all right? So then we'll get mu times x is equal to the integral of mu of t, and I'll just write in those so we know that they're functions of t, dt, and to get x by itself, we would just get x of t is equal to, and we're going to divide by that guy, so 1 over mu of t, and then times the integral of this thing, okay? So it looks really weird with just like variables and things like that in here, but when I show you an example, then it'll become clearer, hopefully. So the other important thing to note, let me get rid of that line there. We'll do this, okay? So you might be wondering, okay, how do we find this integrating or integration factor, this mu of t? That is a very good question. So what we're going to do is actually just utilize this equation here, okay? So when we do that, let's distribute in the mu, okay, into both of these terms. So we get mu times x prime minus mu times ax, all right? That's the left side. That's pretty simple. And then on the right side, we're just going to kind of use the product rule, right? Because each of these are functions of t, and we're taking the first derivative of them. So it'd be mu prime times x plus x prime times mu. All right. So, and we see that these terms, even though they're reversed, so this is the same thing as mu times x prime, right? So we can subtract that from both sides, so these go away, alrighty? And then we're left with this equation here, and we can divide by x on both sides, so those go away as well, and we're left with negative mu times a is equal to mu prime, okay? And each of these are, so this is kind of like a mini separable equation, right? Because we have some kind of d mu over dt, in this case, is equal to negative mu, and these are all functions of t, okay? So then when we solve this, let me continue this on the next slide. I know it does get a bit complicated, because as you can tell, this is just a complicating thing, but if you take it step by step and really understand what's going on, that'll help you in the long run, okay? So let's continue from here on the next slide. So I'll just rewrite it as d mu dt. I'm just flipping it around the equal sign, okay? So minus mu and then times a. Okay, so if we separate these and integrate, we basically just get 1 over mu d mu is equal to negative a dt, and these are functions of t, okay? So when we integrate with respect to each of those, then we get ln of mu of t, of course, and then is equal to the negative integral of a of t dt, okay? So when we solve for this, we just get something like this. Then we just get mu of t is equal to e to the negative integral of a of t dt. All right, and the question is, why don't we have this like plus c there, and then we have a random constant a, or like we've done in the past? And the answer is we do have a plus c, but in this case, we're just trying to find the simplest integrating factor that we can. So we just naturally set our c equal to 0, okay? So we just make that 0, so we don't have to deal with any other like kind of constant in there, okay? So let's get rid of that plus c there. Okay, so this is how you find the integrating factor. If you want, you can just memorize this formula. But you have to remember, because it does get a little tricky with the negative sign there, so you do have to remember this a of t is when we have x prime is equal to a of t times x plus f of t, okay? So it has to be in this form here in order for you to identify your a of t correctly, okay? Like if you subtract it over to the left side and have like x prime minus a times x is equal to f, then it won't be so easy to detect your a because you have this negative sign in front. And right now it's easy because you can say like, well, it's minus a, so you just take this part. But when you actually have like variables and numbers and things in there, it gets a little bit trickier. So make sure you're in this form when you identify your a of t, okay?